Okay, so page 5, we're looking at the remaining total area graphs. And so some of them are very straightforward. You can bang them out immediately. And then there's some of them where it's like, I might have to do a little extra thinking here. We'll start off with the ones that are very straightforward. So looking at numbers 8 and 10, you can just crank those out because it's the same function over an interval. You can just crank those out immediately and be done with it, because if I take the negative area and make it positive through an absolute value, that's all we need. So this would be over the interval of 0 to 4, the integral of the absolute value of 3x minus x squared dx. All right, because again, it takes the negative part of the graph, the negative bounded area, and makes it positive. All right, then adds it to the positive area, and then you're good to go. All right, the same is true for number 10, where we're looking at a function or an interval of 0 to 3. And the function, if we take the absolute value, it would be of 4 minus x squared dx. All right. And so really all we're doing is taking the negative part of the area and making it positive. So, just rough sketch here, but it's going to look something like a little bit of a bow to it, but something along these lines. All right, so this negative area becomes a positive area. Put it all together with this guy here, and you'd have what you're looking for. All right, so that part, those kind of questions should be fine. Actually, I'm going to save numbers 7 and 11 for last, because number 9, it's right adjacent to number 10, so I might as well take a look at it. Under normal circumstances, if I were to just find the area on the interval of pi over 6 to 5 pi over 6, now there's no part of this is below the x-axis, so we don't need absolutes, of sine x dx, area under a curve, that would get the job done. All right, the issue here is that would give us everything. All right, so starting at pi over 6, that would give us all of this. So what I actually want to do is subtract off the area of that rectangle. So if I know the dimensions of that rectangle, I'm in pretty good shape. All right, so 2 ways to handle it. One way would actually be a little base times height action. Another way would be to use an integral to justify that base times height action. All right, this height here is going to be 1/2 because I'm a mathematical genius and I just know. No, it's actually 1/2 because if I plug pi over 6 into sine of x for x, the sine of pi over 6 or sine of 30 degrees is 1/2. Also, don't go to sleep on the fact that sometimes if it looks like it's something, it is that something. It looks like it's about half the distance, so that's not an unreasonable thing. All right. This distance here would be the difference between 5 pi over 6 and pi over 6. So 4 pi over 6, or 2 pi over 3 if you want. So I could say the integral on the interval of pi over 6 to 5 pi over 6 of the sine of x dx minus the base, which is 2 pi over 3, times the height, so the area of that rectangle, a different color, how about? Let's go red for those keeping score at home. Area equals base times height. Base times base? No, base times height is equal to 2 pi over 3 times a half. The halves cancel, and we're left with pi over 3. Just so we have a little bit more elegance to our answer. All right. Now, you may also look at this and say, well, wait a minute, that's the area under a function. So if you wanted to keep it in terms of integrals, I could write still the sine of x dx part of it But then from there, I could subtract off, because this is really, if I make it a line, a horizontal line, this is the line y equals 1/2. So on the interval of pi over 6 to 5 pi over 6, I could find the area bounded between the function 1/2 dx. All right, so either of these will work. It's up to you. As long as you have an integral in your answer, you're fine. And so that leads me to number 7. Right? Because like I'm saying, as long as you have an integral in your answer, you're fine. So it's a question of, well, I'll call it elegance. I mean, I'm not the first one to coin that term when it related to math. It's just the idea that, like, why would you have 10 separate integrals when you could just do it with one, right? So when we look at number 7, you see it's partitioned. One way that I could do it or handle it would be to say, and this ain't gonna be pretty, I could find the area of this guy, which would be going from 0 to 1. I need that to be a positive area though. So the absolute value of x squared minus 1, poor quality, close absolute, dx. All right. Then I could look at this and say, well, I have a rectangular region. Looks like it's going to 2. I mean, it's definitely going to 2. I'm just kind of playing along here. That rectangular region would have a base of 2 and a height of 3. So the whole region has an area equal to 6. So if I add to the integral that we just came up with, 6 minus the area of that null space, the area that contains no area, the area that contains no area. I mean, I'm not wrong. It just doesn't sound too nice. The non-shaded region. Going from 1 to 2, the area between the function x squared, let me keep it red, x squared minus 1 dx. All right, so what that'll do is it'll find this area. Again, I want that in red. It'll find this area and subtract it from the combined area or the total area on that interval above the x-axis of 6, and it'll give me what I'm looking for. All right, so that's a lot. It's kind of fun if you're, you know, kind of spatially driven mathematically. It's kind of like a puzzle. It's like, oh, let's see how many different ways I can come up with a solution here. If this isn't up your alley, then it could be the kind of thing where you're like, well, please stop doing what you're doing, you know. So it is what it is, unfortunately. So took a little screenshot of that because I want to show you a slightly different way of handling it, and it is slightly different, but it is based off of a change in perspective. So let me bring in that figure and rotate it and reflect it. Is it gonna does this app let me reflect it? I guess it doesn't. I thought it did. Interesting. Indeed. I thought that's what those sideways arrows represented. Gonna have to do it the old-fashioned way. So you get out of here and you come in. Oh, what a world. Honestly, I really enjoy the fact that the old-fashioned way is what I just did. That's pretty cool. So what I can do is change my perspective. All right. So I moved some things around. I rotated and reflected the figure so that we're going from negative, I'm just going to make it look a little nicer, -1 to 3, where the y-axis is now the horizontal axis, and going from 0 to 2, where the x-axis is now the vertical axis. All right. So that's gonna require us a change to change the mode in which we're evaluating the function, because now instead of being a quadratic function, this is a root function. All right. We started off with y equals x squared minus 1. If I add 1 to both sides, I get x squared is equal to y plus 1. And if I take the square root of both sides, I get x equals, we only want the positive because it's above the x-axis, square root of y plus 1. All right. Normally I'd say plus or minus, but just like that circle problem 2 or 3 pages ago, if you're not working below the x-axis, then you would not need the negative. All right. So here, this is where the negative would be, the sideways parabola. This one here would be x is equal to negative the square root of y plus 1. All right. And so now what we can do, and this is the really, critical part of the lesson, because it allows you to take something that may have been more complicated than it needed to be, and it actually makes it a whole lot simpler. Because now what I can do is I can say I'm looking for the integral on the interval of -1 to 3 of, this is now going to be that arbitrary rectangle, is going to have a thickness of dy with a height of x. So x times dy, where that x is now equivalent to the square root of y plus 1. All right, so I'd be looking at the integral on the interval of -1 to 3 of the square root of y plus 1 dy. All right, so your final answer, I mean, this is a mess now, but your final answer would either be this bad boy or that little well-behaved boy. I don't know. So yeah, not too bad. The big follow-up question, typical follow-up question, would be, how do I get that answer? I can get the answer for the other way of doing it, but how do I get the answer for this? Put it in your calculator. Just use y instead of x, or use x. It doesn't matter. The calculator is okay with a change of variables as long as you're consistent. So as long as this matches this, you're in good shape. All right, so that brings us to the grand finale. That would be number 11, which, if you look at it, it really is the same as number 7, just a slightly different perspective. And so, like I was saying, change the way you look at things. Now, how do you know when to switch over and look at it from the perspective of y as opposed to x? Well, the answer is look at where the area is bounded. If the entire region that you're interested in is bounded between the function and the x-axis, do it the way we've been doing it. All right, so like numbers 8 and 10. If the entire area is bounded between the function without any gaps between the function and the y-axis, then it's a good idea to change your perspective. All right, so now you can get it without doing the way I'm about to do it, but it's worth giving it a shot to try to understand the concept. All right, so good old-fashioned way of manipulating a diagram. This is definitely going to be easier to manipulate. Just do a slight rotation here. Boop. I remember the days where I had to, this was not the good old-fashioned technique. the days where I had to, on a chalkboard, try to kind of make sense of this. I was telling people to imagine looking through the chalkboard at the paper. I mean, it was interesting. All right, so having an annotation app definitely helps. All right, now it'd be nice if it kept the numbers and letters and everything the way I'd like it, but that's okay. So this is really -9. This is really a 3. This is really a y. This is really an x. And that's a function solve for y in terms of x. All right. So I need the integral on the interval of -9 to 3 of some function solve for x in terms of y dy. All right. So it's the same general idea. I'll just do the work off on the side here. We have y equals, a little bit more involved, but nothing too crazy. All right, so I want to solve for x. So I'm going to swap these two guys. And, you know, I'll swap the signs when I swap them. You know, I can't just change their positions. I'm going to divide both sides by 3. Don't worry about simplifying. Your calculator is more than up to the challenge there. All right. And again, it could be plus or minus, but we're above the x-axis, so we're only going with the plus. All right. So the correct or a correct integral that would give us this bounded area would be the integral on the interval of -9 to 3 of the square root of 3 minus y over 3, that entire expression under the radical. Make sure that you don't leave that 3 out of the